Welcome to our lectures in quantum field theory, and this is now going to be the chapter that we will discuss Klein-Gordon equation in scalar fields. And as we will know, Klein-Gordon equation is just a relativistic form of the Schrödinger equation. This means that we have incorporated special relativity to Schrödinger equation and therefore arrive at Klein-Gordon equation. And this equation actually works on the scalar fields. So together with this lecture, please read Michio Kaku's quantum field theory, F. Mandel and Shaw's quantum field theory, and F. Gauss relativistic quantum mechanics and field theory. There were attempts to merge the theory of relativity, special relativity specifically, with quantum mechanics to make relativistic generalizations of the Schrödinger equation applied to particles. Schrödinger actually derived the relativistic equation, which is the Klein-Gordon equation, before coming up with the famous non-relativistic wave equation, which is the Schrödinger equation. But he discarded the KGE, or Klein-Gordon equation, as the correct one for quantum mechanics for the reasons that it appeared to have solutions with negative energy, and before really negative energy was a taboo, and that particles cannot have negative energy. But eventually we will know that these particles have positive energy, but they're just antiparticles of a particle. I mean, the counterpart, the charge conjugate of a particle. Also, it appeared to lead to a negative probability distribution as well, and it gave an incorrect spectrum to the hydrogen atom. So that's why he discarded Klein-Gordon equation. The only major problem with KGE is a problem in interpretation, actually. And we start with relativity. We treat time and space on equal footing, because like in the Schrödinger equation, space is in the order of second derivative, while time is just first derivative in Schrödinger equation. To say that time and space are on equal footing, this implies that the derivatives applied to time and space coordinates must be of the same order. So like, for example, if you want time to be second order as well as space in the second order derivative, or you make it both first order. In the non-relativistic Schrödinger equation, there is a first order derivative with respect to time, but derivatives with respect to space or spatial coordinates are of second order. Here. So you have a second order in space and a first order in time. Clearly, this equation is not relativistic, since you have different orders of derivative in space and time. So it is first order derivative with respect to time and second order derivative with respect to space on the right side. Now, to incorporate special relativity into quantum theory, we should expect symmetry. This situation is rectified in the Klein-Gordon equation, where the second order derivatives are applied to both time and space. As we will discuss in the next chapter, the Dirac field equation DFE, which applies to spin 1/2 particles, has first order derivatives applied to both space and time. As what I have said, the Dirac field equation applies to spin 1/2 particles. The Klein-Gordon equation will apply to a different kind of particle, and these are the bosons, and these have integer spins. But we will get to that in a while. So the Klein-Gordon equation, or KGE, applies to scalar fields. And the Klein-Gordon equation arrived from the application of two fundamental principles: special relativity and quantum mechanics. These are the relativistic relation between energy, mass, and momentum derived by Einstein, and the promotion of measurable quantities or observables to mathematical operators in quantum mechanics. So actually, Klein-Gordon equation was derived first by Schrödinger and then Klein and Gordon. So by writing down the fundamental relation between energy, momentum, and mass used in special relativity, as we have this, in quantum theory, observables turn into mathematical operators using a specific prescription, and that we're able to find that energy is just an operator, which is a derivative with respect to time, times I h bar. I there is just square root of -1, and h bar is just a Planck's constant. And of course, our momentum is derivative with respect to space times -I h bar. In 3 dimensions, you have a derivative represented by the del operator. So we will substitute this to this 5.4 and 5.6. We will substitute this to here, to this equation, as operators, so that we will be able to arrive at this one here by substituting E squared with -h bar square, second order derivative with respect to time, and then P square changed to -h bar square del square, so that we will have this. And so they're operators. So in order to have meaning, we apply these operators to a function of space and time, which is just this one here. By the way, this thing here, you have x in boldface. That's actually just a 3-dimensional vector, and then you have time not in bold space, but it's actually a 4 vector. Inside is the function phi is a function of space-time, a 4 vector. So anyway, if you write that by hand, phi would just be x, like that. But since we don't have this symbol in the font, we would just make the X there to be I mean in boldface. So finally you will have this as your Klein-Gordon equation. Yeah. So in particle physics we are using natural units, so we use h bar and c to be equal to 1, and then we just when we go to the final result, it will just be we will just fix the units after that when we get the final answer. So anyway, this is now your Klein-Gordon equation in another form, where you now use natural units. Using the D'Alembert operator in Minkowski space, this is just the equivalent operator. That is, the D'Alembert is just equal to the second derivative of time minus del square. And so that your Klein-Gordon equation was simplified to this, but it's too simple. Klein-Gordon equation is actually more popularly known in this form. Note that the D'Alembert is a relativistic invariant, and it is the same in all inertial reference frames because it transforms as scalar. It transforms as a scalar. The mass m is a scalar, so the operator is also a scalar, the one given by the D'Alembert plus m square. So therefore, the Klein-Gordon equation will be covariant provided that the function phi, which is actually just the field, also transforms as a scalar. Note that the coordinates x mu transform as this one here under the Lorentz transformation. If a field phi x is a scalar field, then it transforms, or this is this one now, x is not written in boldface. This means that you're using the 4 vector here, so it transforms as this one. So that leads to the first important characteristics of the Klein-Gordon equation. So it applies to scalar fields or scalar particles, and note these particles are spin 0 particles. Also, using this notation, this one right here, which is also just the same as the D'Alembert, is you can write the Klein-Gordon equation to be like this, which is in quantum field theory the mostly used expression for Klein-Gordon equation. So again, this Klein-Gordon equation describes a free scalar particle. Again, 5.11, equation 5.11 describes a free scalar particle. The free particle solution, as you probably have remembered, is given by this one here, just the momentum without any potential at all. So this is just exponential of negative I, p mu x mu, or you can write it this one as this one. In special relativity, p and x are four vectors given by this one and this one. So momentum is energy, and the three the spatial momentum, and then you have x as coordinates of time and space. And by the way, if you write this by hand, p would just be equal to e, like that, as I told you earlier. And of course x would be t x. And of course when you use the four vector notation, you have x 0 equals time, and x1 2 or 3. This is your usual x, y, or z. So anyway, that's your x. X 1 2 3. And so your p0 will just be energy. So the scalar product of momentum and time will just be this one. As you can see here, it's written that way. The free particle solution implies the relativistic relation between energy, mass, and momentum. For simplicity, we'll just consider here a solution that is in one spatial dimension, so that our partial derivative of phi with respect to time would be given by this one, and the derivative of phi with respect to space also will be given by this one. And so our if you get the difference, this is just this one here, and of course that is equal to the negative mass square. So that will give you the Klein-Gordon equation leading to this one. Then this is just equal to the relativistic equation relating energy, momentum, and mass if you cancel the phi. So if we solve for the energy of phi, then we would have to include both positive and negative square roots, and the energy would be given by this one here. And this is the reason why Schrödinger discarded the Klein-Gordon equation. So the solutions for the energy of the particle says it is possible for a particle to have both positive and negative energy, and at that time negative energy was a non-physical result. And even up to now, we don't really care about the negative energy states. So how about this now? So finding negative energy states was the first indication that the interpretation of the Klein-Gordon equation was as a single particle wave equation is incorrect. But as it turns out, they have to reinterpret Klein-Gordon equation, because if they really wanted to get away with the negative energy, then they would have to reinterpret the particles associated with the negative energy to be antiparticles. That is, particles with the same mass but opposite charge, with positive energy this time. So the second problem with KG is the fact that the time derivatives are second order, which leads to the problem of negative probability densities, which is nonsense in non-relativistic quantum mechanics. But actually the equation is not describing a single particle, but it is describing, it is describing a field. Because usually in non-relativistic Schrödinger equation, we just put the wave function, or assign a wave function to a single particle. But this time, the Klein-Gordon equation is describing a field, not an ordinary particle. So let's go to an example. Show that the Klein-Gordon equation leads to a negative probability density in the free particle case. Just consider one special dimension in this case. So we begin by assuming that the probability current assumes the same form as in quantum mechanics. And while keeping h is equal to 1, define the probability current as this one here. Now if you get the space derivative of the current, or the probability current, then you would get this form. And using the Klein-Gordon equation, we can transform the derivatives with respect to space into time derivatives. So this is your Klein-Gordon equation written in, of course, in a different way, in different arrangement. So if we replace these things with the Klein-Gordon equation, using the Klein-Gordon equation, so you will have this one. That's the equivalent if you follow the expressions there, the solution. Recall that from quantum mechanics, the probability current and probability density rho satisfy a conservation equation called the conservation of probability. This is actually a continuity equation, which becomes, when working with one spatial dimension, this is just this one here. And so if we replace this thing with the one that we got here, so our probability density will be equal to this one. And that since both sides are derivatives with respect to time, we can actually show that the rho is just this one. So you have to try to show it yourself. Be it known that the Klein-Gordon equation includes second order derivatives with respect to time, which leads to a probability density that has a very different form than it takes in quantum mechanics. The probability density is defined in terms of the wave function as this one here. This has, by the way, an exponent of 2. And this is a direct result of the expression found in the probability current, namely this one. I mean, using the Klein-Gordon equation. So the presence of the first order time derivatives in the probability density rho together with the solutions of the energy leads to some problems. Now let's take a look at the free particle solution. So again, recall that the free particle solution is of this form. And again, consider that x there is just one-dimensional space. So the time derivatives of the field, the field phi and the field phi star. Phi star is just a conjugate of phi. So that means that you just change the I with negative i's. So now you will have this expression would be just negative IE, and this one will just have negative, I times E. The energy. So the probability density would be this one. And we have to remember that E is, as we have seen earlier. So in the case of the negative energy solution, this one, the probability density is less than 0, which is a negative probability density, and it does not make sense in quantum mechanics. You have to note that in quantum mechanics, a probability of 1 means the particle is easily found, and probability of 1/2 means that it might be found, or probability of 0 means it cannot be found, and the negative probability has no interpretation at all in quantum mechanics. So in this case, reinterpretation of the Klein-Gordon equation has to be done. So instead of imagining that the equation governs the wave function of a scalar particle, imagine instead that phi is a field, and promote phi to an operator that includes creation and annihilation operators, and create and destroy quanta of the field or particles, and force phi to obey the canonical commutation relations. And so later on we will see that the existence of antiparticles. So we'll now go to field quantization of scalar fields. So we will now quantize the field phi x. Again, x here is a 4 vector x. The process of quantization means creating a quantum theory from a classical one is based on imposing commutation relation or relations. Canonical quantization refers to the process of imposing the commutation relation of position and momentum here, and overall the quantization procedure is to promote position and momentum functions to operators and impose the commutation relation in this one here given by that. So position is it is an operator in quantum mechanics, but it also is an ordinary operator, while momentum involves derivative. it is not so um, clear with the position. Momentum is clearly an operator, but position, yeah, it only what it does is just multiply itself to the function or to the wave function. A similar procedure is followed for quantizing a classical field theory, and in this case, the procedure is called second quantization. In quantum field theory, the fields are quantized rather than quantizing dynamical variables. The problem now is having to put space and time on equal footing. In non-relativistic quantum mechanics, position and momentum are operators where the position operator acts on a wave function according to this. As I've said, it just multiplies itself to the wave function, while the momentum operator acts as this one, a derivative. On the other hand, time is only a parameter in the non-relativistic quantum mechanics, and it is differently treated compared to the position. And this one is actually not true in quantum mechanics. Now, we try to construct a theory based on promoting time to an operator, but that is not what is done in quantum field theory. We take the opposite approach in quantum field theory and demote position and momentum from being operators. They now act as just ordinary parameters that label a position in space-time for a field. So they're now just numbers, not operators anymore in quantum field theory. To quantize the theory, take a different approach and treat the fields themselves as operators. So we now take the fields as operators, but x or the space and time are ordinary parameters. So the procedure of second quantization is therefore to promote the fields to operators and impose equal time commutation relation on the fields and their conjugate momenta. Since the fields are quantized rather than the position and momentum, this procedure now is called the second quantization. The first quantization was used in ordinary quantum mechanics. Now, in quantum field theory, position x and momentum p are not operators, they are just numbers like in classical physics. The fields phi, a function of space-time, and their conjugate momentum fields pi, also a function of space-time, are operators. Canonical commutation relations are imposed on the fields. The fields are operators. There are quantum states in quantum mechanics, but these are states of the field. So, field operators act on these states to destroy or create particles. In quantum mechanics, we do operators like in harmonic oscillator. We apply an operator to increase the energy or decrease the energy. But in this case, in quantum field theory, you are using an operator to destroy and create, or to create particles. This is important because in special relativity, the particle number is not fixed. Hence, particles can be created and destroyed. And to create a particle, at least twice the rest mass energy, E is equal to mc squared, has to be needed. The mathematics that describe the quantum theory with changing particle numbers has its roots in a simple harmonic oscillator. So, by the way, this one is one of the few exactly solvable models. We will review harmonic oscillator, but we will apply the results or the technique in quantum field theory. So in ordinary quantum mechanics, the Hamiltonian of a simple harmonic oscillator is given by this, and that you can solve this by using annihilation and creation operators given by this one. So you can review this from quantum mechanics. So it is straightforward from here that momentum and time, space and momentum commutation relation is equal to I, and that the commutation relation between the annihilation and creation operators is just equal to 1. So the Hamiltonian can be written in terms of these operators and is given by this one here. And we define the number operator as this. So maybe it's if you want to really know details of this, you can review harmonic oscillator as solved in quantum mechanics. So you can rewrite again the Hamiltonian in this form. The Hamiltonian, of course, will satisfy this equation with the eigen values of omega n plus 1/2. Of course, these are the energies here. So in this case, in quantum mechanics, we're talking about states, not particles. They are eigenstates of the number operator n here. N here is just an integer. The number operator obeys the following commutation relation with the annihilation and creation operators. And this is just this one and this one. So of course that can be easily checked. The annihilation operator decreases n by 1 unit, and the creation operator increases n by 1 unit. So you have this in quantum mechanics. There is, of course, a lowest lying state, and its necessary existence because is due to the fact that the system would be able to disintegrate, would be able to into giving negative energy states to the system. But of course, harmonic oscillator doesn't have negative energy. So of course, you have to define a ground state or a vacuum state. Vacuum state means, vacuum state is what is termed in quantum field theory, because you can only say that it's vacuum state when there is no particle there. All the particles are annihilated as a vacuum state. But in quantum mechanics, we say it's a ground state because it's the lowest energy. And as defined, your ground or vacuum state is just this one. So meanwhile, the state n is obtained from the ground state through repeated applications of the creation operator. This is without limits. Unlike going to the bottom energy. So these ideas carry over to quantum field, but with a different interpretation. In quantum mechanics, it is about a single particle with state n and n energy levels En equals omega n plus 1/2. But in quantum field theory, the creation and annihilation operators move the state from one move the state of the particle up and down in energy from the ground. So in quantum field theory, we take the notion of number operator literally, because in quantum mechanics, number operator will just give you an increase or decreased energy, but here a decrease and an increase of number of particles. The state n is not a state of a single particle, rather it is a state of a field with n particles that are present in that particular state. The ground or vacuum state, which is also the lowest energy state, in a state of the field with 0 particles, but the field is still there. But the particles is not, there are 0 particles. However, the creation operator adds a single quantum, a particle, to the field, while the annihilation operator destroys a single quantum or removes a single particle from the field. So in general, there will be creation operators and annihilation operators for particles as well as for antiparticles. These operators are functions of momentum, as we shall see later in the next section. And as you will also see in the next section, the fields become operators written as sums over annihilation and creation operators. So the next thing that we will discuss is about scalar field quantization. So consider a simple case, a real scalar field satisfying the Klein-Gordon equation, which is this one here. So phi is a scalar field. The free field solution of the Klein-Gordon equation is of the form, again, that one. Please remember that. And we write this using the wave number k, and we let our E to be this one, and we change our momentum to k. So the relativistic notation for position is also adopted, and so our wave function or our field becomes this one. So instead of xt here, we have x, because it's now a 4 momentum, and then this one can be easily associated with this one here. Now we can write the general solution to the Klein-Gordon equation in terms of the Fourier expansion. Given by that one there. And now apply step 1 of the quantization process by promoting the field phi x to an operator, and this is done by replacing the Fourier transform of the field phi k and phi star k by annihilation and creation operators associated with each mode. So you can write each mode means each k. So we will replace phi with a with a annihilation operator, and our phi star will be replaced with the creation operator here. So now the field is now an operator. So we write it now with this one. By the way, in our lecture notes, an italicized capital letter or any letter would be would represent operators. So our operator or field is now of this form. As you can see, you have an annihilation operator and a creation operator. So to have a quantum theory, a conjugate momentum to the field is needed so that the commutation relation can be imposed. So we will have to get the derivative of phi with respect to time. So by the way, if you recall this Lagrangian, this leads to the Klein-Gordon equation, of course, and here the conjugate momentum to the field is given by this. So now we will just have to get the time derivative of the field operator, and of course it's easy to follow that starting out with your operator, the field operator, which is this one, gives the conjugate momentum to be of this form. So the commutation relation imposed follow from the canonical commutation relation used in ordinary quantum mechanics. For Cartesian coordinates xi, these are the commutation relation, where the delta ij is the Kronecker delta function. But going to the continuum with spatial locations x and y, we write our Kronecker delta into an ordinary delta distribution, this one here. And so for field operators, our commutation relation would now be this one here. So this commutation relation will only work in quantum field theory. They have different forms in quantum mechanics, but these are the ones valid for quantum field theory. So the next session will now start with an example. So that's all for this lecture. Hope you've learned something today.